So, continuing our look into matrices. Unlike last day, which the focus was just on multiplication of matrices, here we're introducing various ideas that lead to the idea of matrix multiplication. And also, I'd like to apologize in advance. Just getting over a cold, so I'll probably be sniffling and stuff a bit. So, luckily, nothing's contagious over a video, I believe. So, unlike last time, I have a whole bunch of new sort of terms, and instead of me just reading all these are, a lot of them are pretty quick. Right now, one of the most important ones I want to talk about is the determinant, which is in your IB booklet. And it can be calculated for any square matrix. You're only expected to be able to calculate the determinant of a 2 by 2 matrix on your own. For a 2 by 2 matrix, the determinant, which is either denoted like this or like this, is A times B minus B times C. So these two take away these two. And knowing the determinant tells you a few things, describes a few aspects of the matrix, and also allows you to find the multiplicative inverse, which we'll use in a moment. So let's just get straight to it. Here I have a pretty simple square matrix, 1, 2, 3, 4 for matrix A. I want to find the determinant of A and the multiplicative inverse of A. And so the determinant of A, which can be written like this, or the absolute value of A, is quite simply 1 times 4 minus 2 times 3. So 4 minus 6, so negative 2. Now, if the determinant is 0, that tells you that what we call a singular matrix, and that means you can't find a multiplicative inverse. But that's not the case here, so there is an inverse we can use, which we'll use in a bit. That said, let's find that inverse. And so, and now they know the determinant. And so the multiplicative, I'm probably saying that wrong, inverse of A is 1 over the determinant, which in this case negative 2, times, not the matrix as is, times a rearranged matrix, as it's kind of shown right here. And in essence, and again, you're only expected to do this for a 2 by 2 matrix on your own, and this is in your IB booklet. But these two terms are swapped around, and these two terms are in the same place but have the opposite sign. And so in this case, the two terms that are swapped around are the 1 and the 4, so we have a 4 and a 1 right here. And these two terms are just now negative. And now I want to find what this matrix is. Keep in mind I'm multiplying by a scalar, negative 1/2. So I just need to multiply every value here by negative 1/2, which leads me to negative 2, positive 1, positive 3/2, and positive negative 1/2. Now that said, you can also, on your GDC, as soon as you type in a matrix, if you then just write that matrix to the power of negative 1 in your GDC, it will tell you the inverse as well. So make sure you know how to figure this out on your GDC as well, especially, which becomes essential when matrices are more than 2 by 2 matrices. Okay, and keep in mind now, I want to then show that this here really is the multiplicative inverse of this here, which means when I multiply them together, I should get the identity matrix, which is just a diagonal of 1s and everything else 0. And so I'm going to take this and write this as 1, 2, 3, 4 times what we just figured out. So here's A, here's the A to the negative 1, the multiplicative inverse. And while I could use my GDC, it's also a pretty straightforward matrix to multiply. Remember, it'll be this times this, plus this times this, and we kind of work our way through it. In that case, you get 1, and then this times this times this times, oh, sorry, I screwed that up. Oh, I got too much messiness going on. I got too much circled. Anyways, if you do it, for example, you do get 1, 0, 0, 1. Like from my last lesson, it's hard to describe by just highlighting and circling things. But this here is what we call an identity matrix, a square matrix with just 1s going down. And maybe I'll just show, since I did kind of a lousy job of that, where this here came from. So that comes from 3 times 1, which is 3, plus 4 times negative 1/2, which is negative 2, which is 1. All right. So an example of what we call matrix multiplication is like this. I want to solve for A, but these are not real numbers. These are matrices. And this is only possible for this case if these matrices are square and have the same order. Keep in mind, if they're all random orders, we can't multiply them by one another. So assuming that these are all square matrices and I want to solve for matrix A, you may be tempted to, a lot of it's similar to our real number algebra. We talked about subtracting C from both sides. And so, yeah, I can imagine subtracting or adding a matrix of both sides of minus C, in which case that essentially becomes 0 or a 0 matrix. And so I just have A times B on one side, and the other side I have D minus C. Here's where we got to now be extra careful. With real numbers, we'd probably just divide both sides by B. And the order we multiply it by doesn't matter. We want to avoid that. If I want to isolate just A, then I want to imagine I'm going to give myself a bit of space here. I want to imagine multiplying both sides of this matrix by the multiplicative, whatever, matrix of B to both sides, but in the same order. So right here, I have to make sure I write this the same, all to the right of D minus C, and both that combined. The order, again, we multiply matrices matters. Matrix multiplication is not commutative. And so now this part here is an identity matrix. Anytime we have a matrix times its inverse, it's just an identity matrix. Essentially, you can think of it, it just becomes 1. And so that is just A. On the other side, I have this times B to the negative 1. And so unlike with algebra with real numbers, we have to be a little more careful of what order we write our multiplication. In this case, it would be wrong to write this first. All right, so now let's look at this. I have a system. We've seen systems long ago. And I want to show first that it's equivalent to these matrices here. And so how do I show that? Well, with some matrix multiplication. For example, let's leave this for a moment and focus on this. Okay, thinking back from last day, if I want to multiply these two matrices together, well, I can start by going 3 times x plus 2 times y plus negative 1 times z, and all that should equal to 4. So 3x plus 2y minus z should equal to 4. And I can now go to the next row. 1 times x plus 1 times y plus 1 times z should equal to 0. So x plus y plus z should equal 0. And then my last row, negative 2 times, wrong one, negative 2 times x, so negative 2x plus y plus no z's equals 1. So minus 2x plus y plus no, I'll put 0 z, although it's kind of a waste of time, equals 1. And so now notice what I have here is the same thing I have here, which means I can think of this linear system here as this, this series of matrices being multiplied to one another. And so now I want to show how we can actually use matrix multiplication and our GDC to pretty quickly solve this system, or solve this system, however we look at it. And so first, let's take this up here and let's write this, because we're trying to solve for x, y, and z. So let's call this A times x equals B, and we're trying to solve for x. So if I want to solve for x, first, let's write it as, using some matrix algebra, isolate the x there, and then use matrices in our GDC. So let me first start by writing what I've already written down. Ax equals b. Okay, if I want to solve for x, I need to cancel out that matrix of A, which I can do if I multiply both sides in the same order by the multiplicative inverse. So I have this on one side, and I have this on the other. This is an identity matrix. That's just a diagonal of 1s, which means in the end it's going to be just x over here and this. And so now I can use my GDC. and I can type in matrix A, which was just this. But in my matrix, when I actually use the algebra, I'm then going to just type it to the power of -1 times matrix B, both of which should be quite quick to type out. And when I type this into my GDC, I almost immediately get this matrix, 0.1, 1.2, -1.3, which means that's my X, that's my Y, that's my Z. And I would encourage you to check with your GDC. We have our polynomial, a simultaneous polynomial solver, whatever it's called, and you can solve a system like that. It's actually probably a little bit longer than this, but the idea is not about just saving time. It's about understanding different approaches, and make sure you're familiar with both in an HL course. An SL student, you wouldn't have to worry about this at all. But if you're watching this video, you're probably not an SL student. All right, lastly, I want to look at encoding. And we have a message is encoded by first changing each character to a number using the table given. So again, fairly simple. A is a 1, B is a 2, and so on. But then all those values are written in a matrix, and they're multiplied by this encoding matrix. Essentially a bunch of random numbers that make it nearly impossible to break the code because of the sheer number of combinations. And it's multiplied in a way that we have our encoding matrix times the message equals C, and C is the coded matrix. That's what we have here. So this is our message, but it's been encoded. And then really, unless you know this, which again, knowing, we have 9 values here, and the number of possibilities is essentially infinite for what could be there. It's essentially extremely difficult, I'll say, to decode this message. But we have the encoded matrix. So how do we do this? Well, first, let's think about our matrix multiplication here. We have EM equals C. We know C, and we know the encoding matrix. We want to know the message. So how do I figure out the message? Well, a little bit of algebra, matrix algebra. I want to multiply both sides by the inverse of the encoding matrix, but I have to multiply to the left of each side. So on one side I just have M, on the other side I have E to the -1 times C. At this point, our GDC can take care of things, because if I just type in this matrix, but then on my GDC type in, after I have it, E to the power of -1 times, and then just type in this matrix, matrix C, which shouldn't take very long, it will just tell me matrix M, which looks like this: 9, 37, 8, 5, and so on. So again, the only steps I skipped were literally showing me typing this into my calculator. And hopefully by now, you're familiar with how to perform matrix operations on your calculator. And so what is this message? Well, let's see. So first I have 9, which is I. Then 37, which is a space. Then 8, which is an H. And if I keep going through, I get an E, and then I'm just going to work my way through this way. Then I get an A, then I get an R, then I get a T, then I get another space, then I get an M, then I get an A, then I get a T, then I get an H. Oh, look at that. What a nice message. I heard math. All right. And keep in mind, again, ideally we are getting more and more proficient and confident with how to use our GDC to type in matrices, and therefore it can do a lot of the sort of grunt, tedious work of finding the multiplicative inverse and finding these matrices for us, which is, of course, what a calculator is meant to do.